All right, you're on, sir.
Hello, this is Doug Montgomery, and I would like to welcome you to our Fireside chat on the 16th of September. Um, this is number 5 in our Fireside chat sequence. The previous 4 Fireside chats, just like this one, have been recorded on Coursera, and you can find them there in the Resources tab for this course. And this one will get posted as well, so you can take care of this, and watch it later if you'd like, or watch it again if you want to come back and see some of the others. We've got a few new faces showing up today, and so just a couple of reminders. The mics are muted, videos are turned off. Please don't turn them on. We have a guest today, Brad Jones from JMP. And as usual, we're going to have a question and answer session starting about halfway through the chat. And if you have a question for either Brad or for me, or maybe for both of us, please submit that question using the chat function on the Zoom menu bar. And you don't have to wait until the Q&A part starts. You can submit your question anytime you want, anytime during the session. And we'll do our best to answer these during the session. But if we don't get that done, then we'll respond to them offline, and they'll get basically posted in Coursera for the people that are enrolled in the course. The topic that we're going to talk about today is a topic that actually comes up in course number 3. Of the set of courses that we have in Coursera, the one that deals with model building and response surfaces and mixtures. And it's a really interesting topic. And I have a guest that is going to take you through this material. And the guest is Dr. Brad Jones from JMP. He's a distinguished research fellow in the JMP division of SAS. He's responsible for the development and implementation of new design of experiments techniques in JMP. He built the JMP Custom Designer platform, which if you've been following along in the course, you've seen some examples of how to use that through the videos that Carly Metcalf produced. This is a really powerful tool for creating optimal experimental designs. He has a patent on the use of designed experiments for minimizing registration errors in the manufacture of laminated printed circuit boards, and other patents for innovations in the area of experimental design. He's also the inventor of the prediction profiler that you see in JMP, which is a really elegant way to explore the interactive relationships between multiple input response surfaces. He is the co-discoverer with Chris Nachtsheim of the University of Minnesota of something called a definitive screening design. And that is the topic that we're going to discuss today. I think definitive screening designs are one of the most important developments in response surface design methods, really since the original paper by Box and Wilson in 1951. So I think this is a really very important development. He's the author of 2 books with his colleague Peter Goose. He wrote Optimal Design of Experiments, a case study approach, and that book won the 2012 Ziegel Prize, which is given by Technometrics. And he and I are also co-authors of a new book, Design of Experiments, a Modern Approach, which is based all around using optimal design as the framework of creating designs. Brad is the recipient of the Brumbaugh Award. This is the award given by the American Society for Quality for the paper that makes the largest contribution to industrial quality control. And he won this award twice, and one in 2009 and in 2011. He also won the Lloyd Nelson Award, and that's an award given by ASQ for the article having the greatest immediate impact to practitioners. And he won this twice, in 2010 and again in 2012. In 2012, he received the Statistics and Chemistry Award from the American Statistical Association for outstanding collaborative work with a chemist. And he also won the Uden Prize for the best expository paper in technometrics in 2012. Brad is a former editor of the Journal of Quality Technology. He's a fellow of the American Statistical Association. He and I have been colleagues and friends for a very long time, and it is my great pleasure to introduce to you Brad Jones, who is going to talk about definitive screening designs. Brad, wonderful to have you here, and I greatly appreciate your willingness to be a guest for our MOOC.
Well, thanks, Doug, for that great introduction. Let me share my screen and get started with my slideshow. Definitive screen designs is the topic of the day, and these designs were invented relatively recently. Back in 2011, they appeared in print in the Journal of Quality Technology with my friend and colleague, Chris Nachtsheim. At the time, we were working on a different paper that was a generalization of something called minimum aliasing. We were trying to find designs that, while they allowed you to estimate one model, would protect you from bias from a set of extra terms that you do not necessarily want to have to estimate. And in the course of that research, we ended up discovering definitive screening designs, which is a special case of those designs. But it's a very fortunate special case, as you'll see as we go along. So here's the outline of what I'm going to talk about. I'm going to talk a little bit about screening experiments, because my understanding is that you haven't studied that quite yet in this course. Is that right, Doug?
Well, we talked about screening in course 1 and 2, where we talk about experimental design basics and where we talk about factorial and fractional factorial designs. But I think going through what I'm pretty sure you're going to talk about would be a useful reminder of some of those ideas. And we do have people that jump in and out of different courses, so it's very possible that they might be someplace in the sequence of material where they haven't really seen the lectures that I did on screening. So I think you should press on with this.
Okay, happy to do that. So I'm going to start with a little introduction motivation about screening, and then I'm going to talk about a little bit about how you tell whether a screening design is good, or compare a screening to another design to another screening design. And then I'll talk about how we now create definitive screening designs and how we can analyze them automatically. So factor screening is about starting, it's certainly very close to the first thing that you do when you're entering into an experimental program. Generally at that stage, you might do a brainstorming session, and with all of the stakeholders in a process, and come up with a large set of potential factors that might influence the factor or responses that you care about. And then that large number of factors, you're fairly confident that at least some of them are going to be important, but you don't know which are going to be the big hitters in advance. So what you want to do with a screening experiment is winnow down that large set of factors into a smaller set of active factors. Active, but by active I mean they have big effects, and we can do that with a screening experiment. And then, given that smaller group of factors, we can augment our initial runs to learn more about those particular factors. In general, what we want to do primarily is identify active main effects or first order effects. And then secondarily, we might want to also identify a few active second order effects like two-factor interactions or quadratic effects. So what makes a factor important? Well, it's those three things that I was talking about. Having a large main effect certainly makes a factor important. If a factor is also involved in a two-factor interaction effect, which could be either synergistic or antagonistic, that would make it an important factor. And if it has a big curvature in its effect on the response, that would also make it important. So our typical screening assumptions are that, and really screening designs depend quite a bit on these assumptions being true. We generally have quite a few factors that we're screening, and we hope and trust that fewer than half of those factors will be big hitters. Then secondarily, we hope that main effects will be largely and more probable than second order effects. Because generally, we're not going to spend all the resources required to estimate all the second order effects. So if they're active, we don't want them to affect predictions that much. And then finally, we hope that it's true that if both main effects are active, then it's more likely that a two-factor interaction involving those two main effects is active, and less likely that a two-factor interaction exists when neither main effect is active or only one main effect is active. And there's a paper that discusses all three of these that was published in a journal called Complexity in 2006. And basically they studied 113 different experiments to investigate whether these assumptions actually hold water. And although I'm not going to show you the results of their paper, I can just say that the answer is that all of these things actually are more likely than not to be true in a typical screening experiment. So if you see most books and design of experiments talking about screening designs, they generally talk about three particular screening design. Two-level fractional factorial designs of either resolution 3 or 4, and Plackett-Berman designs, which are all three of which are designs that have factors at only 2 levels, and the factors are orthogonal to each other, which means that the effect of one factor doesn't influence the estimate of the effect of another factor. And if all of the factors are continuous, then there may be one or more additional runs that's run at the center value of all the factor ranges. And those are called center runs or center points. Because these are early experiments and because it's desirable not to spend too much money on the first thing that you do, generally these designs are not replicated because of budget constraints. So here's my math slide, required, you know. Here's main effects. Main effects look like this. So this is the intercept term, like the y-intercept, and these beta sub j's are the slopes of the effects of all these the factors. And we have n runs, that's the I subscript. J factor, J goes from 1 to m, so we have m factors. Then if we had the second order model, these effects look a lot like these effects, except that the factors are squared. So those are quadratic effects. And then these effects are the two-factor interactions that involve a product of the level of one factor and the level of another factor for a given run. And these coefficients are called two-factor interaction coefficients. So that's very fast. Typically, screening designs are supersaturated for the full two-factor interaction and quadratic effect model. So what that means is that there are fewer runs in the design of a screening experiment typically than there are parameters that you want to estimate. And so you can't estimate all of them. This is a plot that is in JMP in the diagnostics of experiments, and it's a plot that has three major areas. Over here on the top left, these show correlations between pairs of main effects. This rectangular area shows correlations between main effects and two-factor interactions, and this area shows correlations among the two-factor interactions. The correlation, if the correlation is 0, then the cells are white. Each main effect and each two-factor interaction is completely correlated with itself, so these diagonal squares are all black. The greater the correlation, the darker the cell, and correlation of 1 is going to give you a black cell. So what you want to see in this kind of a plot is a lot of white and not very much black or gray. So here's an example of 4 different screening designs. This one over here has 6 factors. It's showing the 6 main effects and the 6 choose 2 or 15 two-factor interactions. And if you're willing to spend 32 runs to investigate 6 factors, then you can estimate all of these effects independently of each other. But that's kind of expensive to spend 32, more than 5 times as many runs as factors to investigate just 6 factors. Here we have what can happen if you cut this design in half from 32 runs to 16 runs. Now main effects are orthogonal or uncorrelated with each other. Main effects are uncorrelated with two-factor interactions, but unfortunately, two-factor interactions are completely confounded with each other. So if one of the pairs in the confounding is active, you don't know whether it's that interaction or another interaction. This is an interesting design. This is a Plackett-Berman design for 6 factors and 12 runs. And we can see in this case that the main effects are uncorrelated with each other, but main effects are correlated with two-factor interactions, although not completely confounded with them. And two-factor interactions are correlated with each other. So there's a lot of correlation going on in here. But if you're lucky and only main effects matter, then this design can do as well as these other 2 designs in terms of looking at main effects independently of each other. This is a kind of a new design. This is called an efficient foldover design. The other thing I want to point out about this is even though the main effects are a little bit correlated with each other, all the main effects are uncorrelated with two-factor interactions. And this kind of introduces the idea of minimally aliasing. When there are correlations between main effects and two-factor interactions, as in the case of the Plackett-Berman design, those correlations can cause biasing if the two-factor interactions are actually real and if they're not included in the model. So we'd like to avoid that happening. So what we would like is the picture up here where the main effects are uncorrelated with each other, main effects are uncorrelated with two-factor interactions, and two-factor interactions are also uncorrelated with each other. But we want one more thing, and that is not very many runs. Well, the problem here is this is 32 runs for 6 factors. That's not, that's a lot of runs. So something's got to give. There's this dynamic tension between the cost of a design, which is the amount of money that you're going to pay and the amount of time you're going to spend to do the experiment, and then the information that you can get from that experiment. And that's usually the source of a lot of negotiation between the investigation team and management. So the resolution 3 fractional factorial design is the most inexpensive kind of orthogonal design, but it's also the riskiest in the sense that two-factor interactions are completely confounded with main effects. So if a two-factor interaction exists, it can confuse you about what's going on. For the Plackett-Berman design, two-factor interactions are correlated with main effects. And again, if one of these effects is active and you don't find it and put it into your model, then that can bias your estimate of the main effect. Finally, here on the resolution 4 design, the main effects are orthogonal to each other, and they're also orthogonal to all the two-factor interactions. But if you're unlucky enough to have an interaction or maybe two interactions, you don't know what the source, what the causal effect is of the interactions. It might be, in this case, it might be this interaction, or it might be that interaction, or it might be any linear combination of those two things. Another problem with standard screening and designs is if you have all the continuous factors, you can add center points to those designs to detect curvature, and that works, but it doesn't tell you which factor is causing the curvature. Generally, curvature is caused by maybe one or two factors, not all of them. So you'd like to know that, and the standard screening designs can't tell you that. The other thing about standard screening designs is the blocking that you can do with those designs is very restrictive. The number of blocks that you can have can only be a power of 2. So you can have 2 blocks, you can have 4 blocks, you can have 8 blocks, you can have 16 blocks, can't have anything in between. And that's restrictive. Another problem with, with all screening designs is that as the number of factors grows, the number of two-factor interactions grows as the square of the number of factors. So with 6 factors, there are only 15 two-factor interactions, so that's only 21 effects in all. But when you get up to 10 factors, you have 45 two-factor interactions. That's 55 unknown terms, which might be important. That's starting to get scary. So I was talking earlier about aliasing and minimum aliasing, which is what Chris and I were studying when we found definitive screening designs. Let me tell you about what aliasing is and how it's measured. Suppose these X1s here are the main effects and the X2s are the two-factor interactions. And suppose that we want to keep the number of runs small, so we're only going to fit the main effects. In other words, we're going to fit this model here. We're going to ignore this part of the model. Now, if we're wrong about that, the main effect estimates, these beta ones, may be biased. And that is to say, the expected value of your estimate of beta 1 will be beta 1 plus this matrix A times beta 2, which is the true values of the two-factor interactions. This matrix A is called the alias matrix, so that's why we use A for it, A for alias, and it's computed like this way. So you can avoid this aliasing in 2 ways. If you're lucky, beta 2 is all zeros, and then it doesn't matter what A is. The expected value of the estimate of beta 1 is just going to be beta 1. But if beta 2 is not 0, if all the elements in beta 2 are not 0, then this matrix matrix A becomes important. How can we make what we want is for the expected value of the estimate of beta 1 to actually be beta 1. Well, if beta 2 has non-zero elements, the only way that we can make that happen is by making the matrix A have all zeros in it. So that's what minimum aliasing designs try to do. Here's the alias matrix of a 12-run Plackett-Berman design, a 12-run Plackett-Berman design for 6 factors. And you can see that there are aliasings of 1/3 or -1/3 throughout this matrix. What that's saying is the estimate of the main effect of A is equal to the true effect of A plus 1/3 of the effect of B, of the interaction between B and C, minus 1/3 of the interaction between B and D, plus 1/3 of the interaction between B and E. You can see why we want not very many two-factor interactions to be important. But what we also would like is to make these numbers be a lot smaller, or preferably even be 0. So here's what my wish list is for screening designs. I want a small number of runs, that is to say, order of the number of factors, not order of the number of factors squared. I want main effects to be uncorrelated with each other so that any main effect estimate is not influenced by the estimate of any other main effect. I want main effects to be uncorrelated with two-factor interactions. So I want them to be like resolution 4 designs where those two things are not correlated. But unlike resolution 4 designs, I want two-factor interactions not to be confounded with each other. Because if some of them turn out to be important, I want to be able to identify them. And then finally, I'd like to be able to estimate quadratic effects. Now, in a two-level design, you can't do that. A two-level design, you can have an infinite number of curves that go between the lower level and the higher level of a factor. And so, in order to be able to fit a curve, a particular curve, you have to have a level in the middle. So that means we need 3 levels for each factor in a design. And this is the alias matrix that I want to find. I want to find a design that will give me this. If that's the case, then the main effects and the two-factor interactions are correlated. And if you have a design that's a fold-over design, that always happens. So here is a design that does exactly all those things that I wanted. I'm scaling the high and low values of each factor to 1 for high and -1 for low. And let's look at the properties of this design. If we look at the first 2 runs, you can see that whenever a run in row 1 is +1, the run in row 2 is -1. And if we look at all of the pairs of runs in this design, that's always the case. Each even numbered run is the mirror image of each odd number run. So that's what makes a design a fold-over design. Another thing that we can observe from this design is in every pair of runs, one of the factors is at its central level for that pair. So in the first pair of runs, A is at its central level. In the second pair, B is at its central level, and so on and so on. That's this thing here, and the fact that you have a center run at the bottom allows you to estimate all the quadratic effects of all the factors. So this is what the correlation cell plot of a definitive screening design for 6 factors looks like. We have main effects that are uncorrelated with each other. We have main effects that are completely uncorrelated with all the two-factor interactions. And by the way, they're also uncorrelated with all the quadratic effects. And the two-factor interactions are correlated with each other, but they're not confounded with each other. So that means if you have a few two-factor interactions, you're likely to be able to identify them. So what do you get for running a design like this? any active two-factor interaction is not going to affect any estimate of any main effect. Any active two-factor interaction can be uniquely identified and separated from the other two-factor interactions. The same thing is true of any single quadratic effect, as long as that quadratic effect is rather large compared to the noise, maybe 3 times the size of the root mean squared error of the model. And it turns out that if only 3 active factors, or 3 factors are active out of 6 or 7 or 8, if only 3 factors are active, you can fit a full quadratic model in those 3, no matter which 3 they are. So that if you're lucky and only 3 factors are active, then you may be able to skip the second step of the sequential design problem and go right from screening to response surface methods. Okay, let's talk a little bit about how we construct designed experiments. I start with a conference matrix that has as many columns as there are factors. I take that conference matrix and I multiply every entry in that conference matrix by 1, and I add a row of zeros, and that gives you the design that we were talking about. And what you get is all of the properties that I mentioned before, and the number of runs is only 1 more than twice the number of factors. Now, that was design of DSDs for all continuous factors, but as soon as Chris and I published the paper on definitive screening designs for all continuous factors, the first thing we heard from users was, well, what if I have some categorical factors that are at 2 levels? So then we had to write another paper on adding 2-level categorical factors. And so that can be done. And when you do that, you get, instead of having 1 more than twice as many factors, you have to do 2 more than twice as many factors. And also the main effects will be independent of 2-factor interactions just the same way as they were before, but there may be small correlations between the categorical factors and the continuous factors, but so small as to not really affect estimation or model selection. And then the next thing that people asked for after we did supported categorical factors at 2 levels is, well, can we block these designs? And so Chris and I wrote a paper in Technometrics on how to do orthogonal blocking for these designs. And it turns out that you can do orthogonal blocking much more flexibly than you can for standard 2-level designs. In fact, if you have m factors, let's say 6 factors, or maybe in this case 8 factors, I can either have a design with 2 blocks, or I can have a design with 8 blocks, or I can have a design with any number of blocks in between 2 and 8. So that gives me a lot of flexibility in my choice of how many runs in a block and how many blocks to do. We recommended adding a 0 to each block to ensure that you could continue to estimate all the quadratic effects. So the minimum number of runs in a DSD is twice the number of factors. So if you have 6 factors, twice the number of factors plus 1. But so if you have 6 factors, twice that is 12. And if you add 1 for the center run, you'd have 13 runs. But suppose you want more degrees of freedom, maybe for estimating the variance. Well, if you're willing to do 2 additional runs, you can add what Chris and I call fake factors. That is, instead of making a 6-factor DSD, we make a 8-factor DSD. So that has 17 runs, but then we just don't use the last 2 factors. And we end up having now a DSD that has 6 factors, but 4 extra runs. And that can be very beneficial in the analysis. So just to say once more what I've already said twice, and that is that main effects are orthogonal or nearly so if they're categorical factors. Two-factor interactions are uncorrelated with main effects. Quadratic effects are also uncorrelated with main effects. We can accommodate added two-level categorical factors. We can orthogonally block DSDs with lots of flexibility. And for 6 factors or more, the designs can estimate all possible full quadratic models involving 3 or fewer factors. So you might be able to get the ability to estimate a responsiveness model even with a design that can't fit all of the main effects or all the two-factor interactions and quadratic effects. So of course, once you do all of this design work, the question then becomes, well, how do you analyze these designs? People start out by doing stepwise regression or lasso or Danzig selector. All of these tools are modern data analysis tools, but they're all generic. They can be applied to almost any kind of design. What Chris and I wanted to do was find a way of analyzing designs that took advantage of the very special structure that's built into a DSD. So here's a case study that was actually run. There were 5 factors, and the response was the amount of a biomolecule that I can't tell you about because it's proprietary in milligrams per liter of solution. I'm gonna show you this example and jump very shortly. So when would I recommend using a DSD? I would not recommend using them if you have 4 or fewer factors to investigate. Then you should just start maybe with an RSM to begin with. You should use a DSD if most of your factors are continuous. If most of your factors are categorical, then you can probably do a better job with another approach. If you need to be able to afford twice as many runs as factors. You need to be able to run all the factor combinations that the definitive screening design requires. If the shape of the design region looks like this instead of like this, then that means you have constraints on your factor combinations, and the DSD will not work for you. And also, if you expect that you should do a DSD if you expect that there are likely to be factors that have a curved effect on the response or synergistic effects with each other. I wrote a blog on when not to use a DSD, and that's the URL for the blog is at the top of this slide. It's a short blog. It'll only take you 5 minutes to read. And here are the main points. If you shouldn't use a DSD when there are constraints on the design region, when some of the factors are ingredients in a mixture, when you have categorical factors with more than 2 levels, when you have hard to change factors so that you have to do a split plot design or a design that restricts the randomization of the runs, or when you have a model with higher order effects than second order effects that you want to be able to fit. And now for some shameless promotion. Here's a book that Doug and I wrote and is available now at Wiley. It discusses the approach that you would use when you can't use a DSD and you have to do something more complex. And that approach is built into the custom designer within JMP. Okay, so let me go to my case study. Actually, before I show you the case study, let me show you a paper that was written by, this is the first paper that was written as a case study on definitive screening designs. And I want to read the first sentence or 2 of the conclusions of this paper. So what they did, they used definitive screening designs were used to efficiently select a model describing the formulation of a protein under clinical development. The ability of the single definitive screening design to identify and model all the active effects obviated the need for further experimentation, reducing the total number of experimental runs required to 17 from the greater than 70 runs that would have been necessary using the traditional screening followed by RSM approach. So they were able to, they were lucky in the sense that I talked about before. They found a adequate model, even though they had way more than 3 factors. Okay, now here's the example that I wanted to show you. This is another experiment that was run using the same set of researchers, just a different experiment. So in JMP, if you want to create a definitive screening design, you just go to the DOE menu, and the third element on the DOE menu is definitive screening design. And then you just say how many factors you want. Those are the continuous ones. You can add a couple of categorical ones, and then continue. And then it asks you if you want to have blocks, and if you want to do extra runs. And then you say make design, and boom, that's the design. You can also build into the same menu is fit definitive screening, and that is an automatic that implements the paper, the methodology that Chris and I described in that paper that I showed you in the slides. But when you create a definitive screening design using JMP, it puts a little script in the data table. And that script will analyze the data using the response that you specify. Here are the 5 factors. Here's the response. That script will just automatically fit the model for that response on these factors. And it does it in 2 stages. The first stage is it looks at the main effects. And then the second stage is it looks at the 2-factor interactions and quadratic effects. And then it combines the 2 stages to get the full model. And then you can click this button, which is equivalent to just running a fit model on the design you just found, and you can look at profilers that show the effects. You can see that there's a big interaction between %DO and pH and feed rate here. And then another thing that you can do is you can save columns, and I saved a column of predictive values. Now, I want to show you that the predicted, the root mean squared error of the model here is 40. So you would expect half the runs to be within 40 of the predicted value in a confirmation run. And these guys did 3 confirmation runs. So, and here are the, so they did these extra 3 runs and got the data for them. Here are the values predicted from the model that they found. You can see that this number here is 452 and this is 432. So we're 20 away from the correct answer. Here, 438 and 422. Now we're only 16 away from the correct answer. And this is 368 and 338, which is only 30 away from the correct answer. So all of the confirmation runs are within 1 standard deviation of their predicted value. That would sort of add a lot of, make you feel very good about the model that you just created. So that's all I have for you on right now. I'm open to questions. And should I stop sharing my screen, Doug?
Yeah, let's.
Okay. Here we go.
Okay, well, Brad, thank you very much for really a very enlightening presentation. We discussed these designs a little bit in the course, and they're also discussed in my design book. And there's an example there, but this is very informative, and I really appreciate your taking time to spend with us today. That's great. So do we have any questions? Let's see. Looks like we've got one. It says, I'm running a design experiment on a dispense system for an oligosynthesizer, DNA printer. And the goal is to do a robust design to minimize variability of the dispensed volume, with a secondary goal of using the regression model as the basis for calibration curves. It's a categorical factor of liquid type, and each liquid type can have a vastly different viscosity, densities, evaporation rates, which impact the response. And so, the question is, how do I handle these dependent factors that are uncontrolled? If I dispense with a new liquid of known viscosity, density, and evaporation rate, I'd like to have a close estimate of the dispensed volume. So, Brad, let's think about this. If these are properties of the material that you can measure, but maybe not control, you could treat these as covariates. Is that comes to mind right away? Maybe I don't quite understand the question, but it looks to me like you might be able to treat these as covariates.
Yeah, I think you might be able to do that. It would depend on how different the values for each type is. If the covariates vary very tightly around each material type, and the material types are very different, then it would be very hard to see what the effects of those covariates are. But if the covariates change a lot, and one way that you can make them change is you could alter the viscosity by adding some other inert thing that just makes the viscosity smaller.
Yeah.
So you might be able to spike the material in a way to lower its viscosity.
Yeah.
That might allow you to separately estimate the viscosity while also learning what the effect of the material type.
Material is, right. Yeah,
so
this sounds
material
like
as a cat.
I'm sorry.
You could think of the material type as a categorical factor, and if there are only two different materials, then that would be like just adding a two-level categorical factor.
Exactly. Yeah. Yeah. If you have more materials, then it's a little bit more complicated, and nothing in the DSD family would actually really work. So here's another question.
Unless you're willing to do replicate the DSD for every level of the
you could do that. So is it possible to add a demo tutorial on augmenting custom designs in JMP? Say I want to add a point or points to estimate pure error and or curvature. Many thanks. Brad, I suspect that there is something in the library of wonderful stuff that you have on the JMP homepage that talks about design augmentation. Is that true?
I think so, but I didn't create the tutorial, but I could show you very quickly how that's done.
Oh, sure. That would be great.
So, here's our experiment. Let's suppose that we wanted to do some additional runs. If we go to DOE and say augment design, then here are our factors that we want to look at. And here's here's our response. So that's all the setup that's required. And then there are lots of choices. You could just add center runs. That would allow you to estimate the error variance. You could fold over. You could replicate some runs, but typically what you want to do is just augment for a. You might want to say, let's say I want to be able to estimate all the interactions among these 4 effects. So I'm just going to add those to my model. And then then JMP will tell you how many runs you need to be able to do. If you might say, well, I only want to do 17 runs, and it tells you, well, you can do that with 17 runs. So you would only have to do two more runs to be able to estimate all those extra things. Those are the kinds of things that you can do with augment design. It's a very quick demo.
We in the course we talk a little bit about augmenting designs in the second course that deals with factorial and fractional factorial designs, but the kind of augmentation we're doing there is typically of the fold over type, which helps you separate main effects from 2-factor interactions in resolution 3 designs, for example. So there is some material in the course that talks about this as well. I don't think we have any more questions, if I'm right. Brad, could you spend a couple of minutes talking about sort of what you think some of the more important areas are for experimental design in terms of what needs to be done? What are some of the things out there that people want to do that we still don't have the best methodology for them to use? Where do the researchers in this field need to be going?
Well, right now, JMP, for instance, has designs that allow for random blocking factors, split plot designs, split plot designs, and strip plot designs. Those are all designs that involve blocking factors where you might have 2 blocking factors that are crossed or 2 blocking factors that are nested, and you have runs that you might have set factors that have to stay constant within a block, and so on. That supports a certain amount of complexity, but more generally, you would like to be able to define any kind of unit structure. You might have multiple nesting as you go through, say, a semiconductor process, and you have multiple machines that the units are going through. You might have to split the units twice, 3 times, 4 times, 5 times, and doing that in a very general way is an area that's I think a research problem.
Brad, we have two more questions that popped in. I think both of them are addressed to you. The first one says, can missing values be evaluated in DSDs?
They can be, you can have a missing value coming out of a DSD. Those kinds of things happen. At that point, you would not be able to use the automated procedure, but you could do what people usually do, which is stepwise regression or some other regression technique. And then if you wanted to cheat a little bit, you could take the predicted value that you got for the missing observation and plug it in to the data table and see what the automated procedure would give you. And
That's what I would recommend. That would probably that'd be a good place to start.
well, it is cheating a little bit.
Yeah, but it's a good place to start. And so here's another question. It says, I tried to make fractional factorial design using JMP, and I could get D efficiency about 77%. My colleague brought a very similar but slightly different design, arguable using AI, and its D efficiency was 100%. Is there a field that sort of uses DOE and AI together?
I think that there are a lot of things built into the designer in JMP that are arguably AI.
Yeah.
There are lots of fancy tools in AI. Generally, the problem with trying to use AI type tools in design of experiments is that they don't understand the nature of the problem. There's a lot of superstructure in design of experiments, and AI tends to be more of a generic approach. So I don't know the particular problem that you were addressing, and I would be very interested with seeing the example, because the D efficiency of 77 in a fractional factorial design is very low.
Yeah, I would expect you could get a much higher D efficiency.
So it's possible that you had a sample size that was not a multiple of 4, say.
Yeah, it could be some peculiarity of the sample size.
But even then, I certainly would like to see the example.
Yeah. So this is going to be our final question. Hi, Bradley. How do you calculate the R values, the grayscale, in the correlation plot? And for an alias pattern, I've seen them written as, for example, A arrow A plus BCD. Does that mean that A is the sum of the A factor effect plus the BCD interaction effect? Or is that the wrong way to think about alias patterns? Well, I know in my textbook, I use that arrow notation. And I mean it when I do it. It means that A is completely confounded with BCD, for example.
That's correct. And so what that means is that the correlation between A and BCD is 1. So you would see a black cell for A and another black cell for the BCD interaction, if you were looking at that. Yeah. And in that case, they're completely aliased.
Yeah. And
so if you formed a column for BCD and you formed the column for A, they would contain either exactly the same numbers, or BCD might be -1 times A.
Right, they'd be the negative.
As we look at the absolute value of the correlation.
And the R values in that correlation, they're just simple pairwise correlations.
That's right.
And maybe we'll try to sneak in one more. I work as a manufacturing plant simulation engineer. Technomatics tool by Siemens. We have a feature called Experiment Manager. Do you really see applications of DOE in design of material flow? People have been doing that in the semiconductor industry for decades. I mean, that's how a lot of scheduling is actually done in semiconductor manufacturing. Is they run these computer models, and then they do experiments to try to find the optimum sequence. So I think there's a lot of applications. We got to quit. We're running out of time. I want to thank you for joining today's Fireside Chat. The next one will be Wednesday, 21 October. 11 a.m. Mountain Standard Time, and I will have a very special guest for that session as well. It'll be Dr. Ray Hill from the Air Force Institute of Technology. And for those of you that are in Coursera, as usual, the meeting information will be posted prior. If you're new and want to join, please email Megan Gibson at megan.gibson@asu.edu to get the session information. And as usual, I'd like to thank everybody involved in helping produce this set of materials, and in particular, Dustin Hampton and Megan Gibson, who have done such a wonderful job of managing today's Fireside Chat. Thank you.